Okay, so let me make sure my volume's up here. It wasn't. It's a good thing I did that. Okay, so today what I wanted to talk about with you guys about is basically just our equations that we have for position, velocity, and acceleration. So what I want you guys to start out with is think back to the calculus we just talked about. Okay, and we've got one equation which is a really simple one. Okay, um, our acceleration equation. Acceleration at any point in time. You might hear me call it final acceleration, right? What we're going to talk about is we have a bunch of terms we could put in there. There's a lot we won't put in there right now, like jerk, snap, crackle, and pop. We won't put in those. All of those things are rates of change of this, right? So jerk is the rate of change of acceleration. Snap is the rate of change of jerk. Crackle is the rate of change of yeah. Anyway, you get the point, right? Snap, crackle, pop. Each one goes to a higher, level of this thing. So what I don't want to get into is all that crazy stuff because honestly, we're not going to need to use it. But for us, we will need acceleration, we will need velocity, and we will need position. Those three things will absolutely come up. Okay. If you want to talk about jerk later on, we certainly can. Okay. But realize it's just a change in the acceleration. So I'm going to start off with a super easy equation for you. Okay. We're going to assume that generally speaking, we have a constant acceleration. Okay. Occasionally, we might even throw in a jerk term, and the J stands for jerk here. So that would be our acceleration equation. And I tell you what, let's go ahead and bring that on down, and I'll show you what it looks like, and then we can get rid of it later, and I'll show you the simplified version that you actually need to know, okay? So what I want you guys to do, this is the one equation to rule them all. Seems like a pretty simple equation, right? So it actually gets pretty easy if you're doing calculus with this, which physicists have to do, right? So what I want to do now is I want to figure out how in the heck we're going to find our velocity and our position from this. Well, if you know that acceleration is basically just the change in velocity over the change in time, then all of a sudden you can figure out how to get to velocity, right? This is the derivative of velocity. So to undo a derivative, we have to take an integral. So if I take the integral of this thing, realize we have two terms. We have 1 and 2, right? So we're going to have to use the sum rule on this one. Okay, so I'm going to have to take two different integrals and then add them back together. Okay, and what that will get us, the integral of velocity, or the integral of acceleration is going to be velocity. So if I take the integral of a with respect to t, okay, because we're going to take it with respect to time here. Okay, so remember, this, anytime you see something without the variable you're looking at for an integral or for a derivative, it's actually there, but it's to the 0 power. Okay? So what do? Well, my constant, at least in terms of looking at it with change to time, right? My constant just follows on through, and I multiply by the variable with the power raised by 1. It was at 0, so if I raise it by 1, now it becomes t to the first, or just t. Okay? So I'm also going to take the integral of this guy. Now, it did have a t to the first power, okay, so the constant j comes on through, and I multiply it by this with the power raised to 1, okay, raised by 1, I'm sorry, and also on this one I didn't show it, but I divided by the new power, which is 1, so I divide by 1, so it's just still at. But in this case, if I divide by the new power, I've got j times t squared over 2, or 1/2 jt squared. Okay? And in fact, I'm going to write it that way because that's the way we're going to see it in class a lot. So I'm going to move that half factor out to the front. There it is, 1/2 times j times t squared. Okay? Now, the other thing that I do when I take an indefinite integral, which this is because I don't know where I'm taking this to. I don't know if I'm taking it from 0 to infinity or 1 to 5 or anything else, right? So I have to take and add in a constant. All right? Now, this is the interesting thing. The constant here is actually going to be related to what your term actually is, right? It's going to be a shift in that term. So instead of calling it a c here, I'm going to change that c, that constant that was super important before, I'm going to call this our initial condition for velocity, or velocity initial. Okay? So whenever you see an I on there, that I means initial. If you see an F, it basically means where we're going to look at the end of the time period that we're discussing, right? So you might see me write it as V of t, or you might see me write it as V final, okay? So you'll see these two interchangeably used by me, and maybe that's right, maybe that's wrong, but it'll be the final time that you actually look at for that period, okay? So again, we have A with t bumped up by 1, jerk with t bumped up by 1, and the 1/2 piece, right? Plus our new constant. And we've labeled that constant here. It has to do with velocity, and it was the initial condition of the velocity. So what initial velocity we had, okay? But that's not all. We can go farther with this, okay? And something else important to know is that velocity is the derivative of position with respect to time. And if you think about this, you know it, right? You know this because if I said miles per hour, that would be distance over time, wouldn't it? So therefore, our velocity, right, is that with the direction. So we're going to take a look at the position with respect to time. That's what velocity is. So if we take the integral of this, we're going to undo this. So the thing we're going to find is our position final, or our position, if you want to put it in other terms, right, it's a function of time. So if I look at x at 1 second, 2 seconds, 3 seconds, I can find the position at that time. Same thing for velocity, same thing for acceleration. I can find all of these for 1 second in, 2 seconds in, 3 seconds in. Or if you want to consider that 1 second, 2 seconds, 3 seconds your final condition, you could just call it A final, V final, or X final. Okay? So my final position, or position at a certain time, is dependent upon, well, let's take a look. Okay, so we have A times T here. We have to take the integral of all these things because they're all added up, aren't they? Okay, so this is T to the first. So again, A comes on through because it's a constant with respect to time, right? We're not changing A here. We're changing T here. So A comes on through again. T gets raised by a power, and then the whole thing gets divided by 2, which I'm going to put in front as a 1/2. Okay, 1/2 AT squared. And I could write that better, so I will, so you guys can see it clearly. Okay, 1/2 times A times T squared. And remember on this, only the T is squared. Okay? So what about my jerk term? Well, I had a 1/2. That's a constant. It's a number. And I have a j, which is a constant with respect to time. That comes on through. But now I have my t. I need to take an integral of this guy. So it was t squared. So now it becomes t to the third. And now I also multiply this thing by 1/3. Or I could divide the whole thing by 3. Same difference, right? So let's go ahead and simplify that down. Okay, I got a 1/2 and I got a 1/3. So if I multiply those together, I'll get a 1/6. Okay? So I had velocity before, and again, that was a constant, so it seems like maybe you don't do much with that. But remember, mathematician trick, physicist trick, you can always add in a t to the 0, right? I wouldn't worry about that for using this equation, but when you're integrating it, you have to remember that it's a t to the 0 can always be thrown in. So if I bring that along, velocity initial, well, that just comes along for the ride because it was a constant, right? But the time is not a constant with respect to time, okay? So that gets bumped up by 1, and you divide by 1, right? So let's simplify this down. I'm going to simplify that down. Remember that t to the 0 can be thrown in anytime you like, okay? So here's my new equation for position, but we're not quite done yet, are we? Because we took an indefinite integral again. So we also, again, have to add in, and I'm going to get rid of this so I can have some room. So rewind it if you need, okay? We also have to add in our constant. And the constant is a shift in the original location of our variable that we're actually looking at the moment, right? So in terms of this really should be a position, and really it was the initial condition, so it's xi, x initial, okay? And again, if you want to call this x final instead of x to the t, you can. I'm going to pretty these things up a little bit, okay? So if you include jerk, or the change in acceleration, if you include that in your equation, which we don't always have to worry about, but if you do, then you get these different equations. The equations we're actually going to look at, we don't really worry about jerk most of the time. So I tell you what, first, before I do anything else, I'm going to show you the equations we actually use all the time, okay? I'm going to get rid of jerk out of here because most of the time we have a constant acceleration. But in case you need it, don't forget this, okay? So you might want to write that down in your notes. Here I go, simplifying our equations. Okay, and this is starting to look a little bit easier. Acceleration equation looks not very crazy at all, okay? But I'm going to start by putting my constants up in the front, okay? Why? That's just how you tend to see these things. Okay, so I'm just going to rearrange this stuff in here. And again, I'm going to take and put my things in order of my t, right? I'm going to put it as t to the lowest power, t to the middle power, and t to the highest power, okay? Again, this is just how you see it in physics. It may mess you up, though, because you'll notice that as I write this out, this last one is actually a quadratic equation. I'm sure you all loved hearing that, right? Something that everyone loves. And so there you go. Those are the classic three equations that you take for position, velocity, and acceleration in physics, okay? This is in one dimension. So what does it look like for the y dimension? We talk about the x dimension right now. Well, guess what? It's the exact same thing, but instead of talking about it in terms of x, you'd be talking about it in terms of y. You could still have an acceleration in the y direction, or you could possibly have an acceleration in the x direction. Those two directions, and this is key, guys, what happens in the x does not necessarily happen in the y. And in fact, if I throw something, I give it, see that nice parabolic trajectory? Which you'll notice, if you slow it down and redo this, you'll notice that the x direction is changing at a constant rate. It has a constant velocity. There's no acceleration once it leaves my hand. But in the y direction, you're going to see that it goes up, stops, and comes back down faster and faster and faster. So it slows down, stops, and then speeds up as it falls back down. So the x and the y are totally different dimensions. Never confuse them. Never put them together. Ever. And this is why we went over all that vector math to begin with. You're going to have to split up any kind of a vector that's in both directions. You're going to have to split it up into an x component and into a y component when we're on Earth, or really any planet, right? Or any kind of gravitational influence. You have to split the two up because they're doing very different things, okay? If you want to figure out where this guy's going to end at the end, you cannot have them as a single vector. It will not work because different things are happening this way than this way, okay? So, having said all of that, there's our position equation. How do we use it? Well, let me give you an example. Let's say that we are going to drop something. Our acceleration due to gravity is negative, because it's down, right? Negative 9.81 meters per second squared. And if you talk about this in terms of the magnitude, right, you just talk about it as basically 10 or 9.81 meters per second squared, right? But if you're talking about it with a direction, remember it is negative, generally speaking, because you're falling with it. Now, could this be flipped on its head? If you're standing on your head and I drop this thing, it's going to look like it's falling in a positive direction. So yes, it can. The general convention says it's going to be negative because it's towards the ground, okay? So, we've got an acceleration. I'm going to drop this marker, okay? And in fact, let's make that our example. I'm going to drop this marker. We only have one dimension of motion. It turns out it's the vertical dimension, okay? But when I let it go, what initial velocity does it have? That's a good question, isn't it? I would say, looking at that marker, it has no movement whatsoever in the y direction. It has none to begin with. No initial velocity. Okay? It has gravity trying to pull it down, and the minute I remove my hand, it will fall. Okay? But what about its initial position? Well, I don't have a ruler up here, do I? So I could say that this thing starts out with an initial position of 10 meters, or 5 meters, or 1 meter, or 0 meters. It's kind of up to me and my frame of reference. If I have a ruler and somebody tells me otherwise, then I've got to make a choice. But let's go ahead and assume that the ground that I'm standing on here is actually 0. And let's assume that the height I'm holding it out is about 6 feet. It's about the same height as me, right? So let's go ahead and make it easy and call it 2 meters. It's not quite 2 meters. 6.6 feet would be about 2 meters. But let's go ahead and call it 2 meters for ease, okay? By the way, what I would do for you, generally speaking, especially in the x direction, and again, I guess we're talking about y here, right? But same difference. I'm going to put it as x because that's what our equation looks like. But in our x direction, if nobody's giving you a starting point, the easiest thing you can generally do is make your initial point 0. And again, it kind of takes out some terms and makes it easier to solve for things like time, possibly using this equation. Okay. So, we have a problem now. I'm going to hold this marker, and I'm going to let it fall. It starts out at 2 meters high. It starts out with a gravitational pull of negative 9.81 meters per second, and it starts out with a velocity of 0. So let's take a look. What do we want to find out? Well, if we want to figure out where it's going to be after 1 second, right, or x final after 1 second, we need to know our initial position, right? And guys, this is another thing I would do for you. A good strategy to have until you get comfortable with this may actually be writing out all of these equations and then erasing that term and replacing it with a number. If you feel totally comfortable with it, don't do that, okay? Just go for it. Okay, can we get that on the board? Barely. Okay, so 1/2 AT squared out here, velocity initial times time, x initial. Let's replace those with their actual values. Okay, so for time 0, before I let it go, we start out with an initial height of 2 meters. We start out with an initial velocity of 0. So that's easy, isn't it? Right? 0 meters per second, that whole thing's going to go away. Simplifies it down. You can see why doing that for the position could also be good. And we know our acceleration. Now be careful, because only time gets squared here. Acceleration does not, the 1/2 does not. Only the time, okay? So we got a 1/2, and we got a negative times a negative 9.81 meters per second squared, and times our time squared, okay? And again, now I'm telling you how long has it been. It's been 1 second. So I can plug that in for my time. So it's really 1 second squared. Well, that makes it easy too, because now we can simplify it down. All right, so x at 1 second, what is the position of this thing after it's been falling for 1 second? It started out with a positive height, okay? 2 meters. Velocity no longer matters because it's 0 to begin with, so it goes away. So now we have to consider our acceleration term. We're going to have negative 4.905 meters per second squared, because it's 1/2 times negative 9.81, right? And then times 1 squared, which is, again, just going to keep the same number. So now where's it going to be? Well, it's going to be hitting the ground because we have a ground there. But if it did not have a ground there to stop it, right, which this term does not consider that other acceleration that would be in the other direction, right, to stop the thing. If we didn't have a ground here, or if I'm dropping it off a cliff, where would it be? 2 meters plus, and again, we had time squared here, right? So the second squared will cancel out. Leaves me with a minus 4.905 meters. So I end up with an x position after 1 second of falling from 2 meters. I end up with a negative 2.905 meter position. It would be lower than the ground I'm standing on after 1 second. That's how quickly it falls. Which is kind of cool. So that's what the x position looks like after 1 second. What does velocity look like after 1 second? Okay, I'm going to erase all this. Again, you can review it if you need to. All right? So velocity after 1 second, that's our v final here, right? You might even see me write it quite often as v final, right, with that funny F for final. But after 1 second, our velocity, well, again, our velocity to start out was 0, right? So our initial velocity was 0. And our acceleration, well, that doesn't ever change on Earth, at least, in the y direction, right? So I have plus negative 9.81 meters per second squared. And then I've got to times my time, which is 1 second. Okay, so that'll get rid of one of my seconds on the bottom, right? So now it's just meters per second, which is convenient. We want it with velocity, right? So it turns out we started with 0, and after 1 second, we get a final velocity, after 1 second, of, no surprise here, 9.81 meters per second squared. And that makes sense, right? Every second that goes by, we're going to add another 9.81 meters per second to it. Now be careful, because after half a second, we're still scaling this thing. After half a second, you get a constant change of this thing. Remember, it is a derivative, okay, of the position. So you're getting the rate of change, and it is an exponential change with an acceleration of your position over time. So your position will change not in a linear fashion, but in an exponential fashion, whereas your velocity over time will change in a linear fashion, okay? So another caution for you. After a quarter of a second, you're not going to go the full, negative 2 point whatever meters or a quarter of that. You're going to go some tiny fraction of that because it's still speeding up. After half a second, you're going to go less than half because it's still speeding up. And at some point, it's going to push a lot farther in the second half of that second, right? You're going to speed up more than that every second, okay? Nonlinear rate, exponential rate. Okay, and our acceleration here, well, that's simple, okay? That one's super easy. And I should have taken the second squared off the bottom of the last one. Sorry about that. Have it. All right, so our acceleration is super easy. After 1 second, it's consistent. It doesn't matter if I drop it from here or here. It's always going to be the same acceleration rate. After however many seconds, your acceleration is constant. When does that change? That's a good question. When would our acceleration change and under what circumstances? Think about it in terms of the x, think about it in terms of the y, and I want you guys to tell me where you could have a possible changing acceleration rate. Let's have a discussion about it, okay? That's all I got, guys, all right? Let me log back in so I can then stop the thing. Okay,